Hi, everyone. So last week we talked about linear systems and how to set them up and these different forms of augmented matrices that would allow us to easily read off a solution to a linear system or give the general solution to the linear system. Now we're going to talk about this algorithm that I've mentioned a few times, the Gauss-Jordan algorithm, to actually get from the initial augmented matrix to an equivalent one that preserves those solutions, like we talked about in the lecture a couple of days ago. All right, so the first part of Gauss-Jordan elimination is forward elimination or Gaussian elimination. And I should say, and I made a comment about this in the as an instructor's note in the text. In the West, we call this Gaussian elimination or Gauss-Jordan elimination. Something like 2,000 years before Gauss developed this algorithm, it had already been known to the Chinese. And there's a really nice article that I found about it, and I put a link in the very top of the Zybook section about this algorithm. Anyway, so how is this going to work? Well, the goal with Gaussian elimination is to get a initial augmented matrix for some linear system and get that transformed into a matrix in echelon form. And there's in Gaussian elimination, there is a specific algorithm for how we do this. So I'm going to write down the algorithm, and then we'll do a couple of examples, and I think we'll be good. Okay, so the first thing to do is find the pivot. So the pivot for them is the first non-zero entry in the column. Right, so in the current pivot column. To do this, you might need to swap two rows. And if there are no non-zero entries in the column that you're looking at, then you just move on to the next column. All right, so let me just start an example, I think, just so we can have something to point at. How about this? So let's take an augmented matrix like this one and just start with this first step. So the idea is we're going to find the pivot. That's the first non-zero entry in the current pivot column. So when we start this, we start with the first column. So we're going to look for the first non-zero entry. That's this guy. So this is our pivot column, and that's our actual pivot that we're going to work on for right now. In this case, this is a non-zero entry, so we didn't need to swap. Okay, so after you find that current pivot, the next thing you're going to do is use elementary row operations to get zeros underneath the pivot that you're looking at. And here's a hint. The elementary row operation that you're going to use to do this always looks the same. So if you're trying to zero out the entry in row n, you're going to take row n and you're going to add or subtract some multiple of the pivot row and replace your row n with that. So let's start here. So now I'm going to start writing down instructions like this with the goal of zeroing out entries below the pivot. So that means I want this to be a 0 and I want that to be a 0. And I'm going to use elementary row operations to make sure that that happens, because if I do the elementary row operations, I know I'm not changing the solutions to the linear system that this augmented matrix represents. All right, so what I'm going to do here, I want to zero out row 2, so I'll take row 2 and I'm going to subtract 2 times row 1. So we're going to leave the pivot row alone. Pivot row is just the row with the pivot in it. So this says I'm going to take this second row and subtract 2 times the corresponding entries in the first row. So I'll have 4 minus 2 times 2, so that'll be 0. And 1 minus 2 times 2, so that'll be negative 3. 0 minus 2 times 1, negative 2, and 5 minus 2 times 0 is still 5. All right, so you'll see now, right, this guy has been zeroed out. That was our goal. Okay, so now we need to work on this other entry that's still below our current pivot. It's a -6, and I want to think about what multiple of 2 do I need to add or subtract to -6 to get 0. And that would be 3. So if I do R2 plus 3 times R1, oops, sorry, that's supposed to be R3. So row 3 plus 3 times row 1 should give me what I'm looking for. So -6 plus 3 times 2, that's 0. And -3 plus 3 times 2, that's going to be -3 plus 6, so that's +3. And 1 plus 3 times 1, that'll be 4. And 4 plus 3 times 0, that's still 4. All right, and so now we've got this other thing turned into a 0. I've zeroed out that entry, but I've done it in a legal way, right? I've used elementary row operations to do it. So now, after we've done that, we're just going to repeat this process. So now what we're going to do is move on to the submatrix that's below and to the right of the pivot. So if we call this step 1, step 2, step 3 is to move on to the submatrix below the right of the pivot and start. All right, so the submatrix I'm referring to is below and to the right of that pivot. So this was our pivot. So now we're going to go to the submatrix, which is that's below and to the right of this guy, and just follow that algorithm again. So we identify the pivot. It's going to be the first non-zero entry in this submatrix, in the first column of this submatrix. So this is going to now be our pivot. And now we just have to zero out this 3 that's beneath it, right? That's what the algorithm says. You use elementary row operations to zero out entries below the pivot. I'm starting with R3, and I want to think of what do I need to add, what multiple of -3 do I need to add or subtract from 3 to get that to be 0? Well, I can just add a -3 to 3 and I'll be all set. So this is all I need to do in this one. And what I'm going to end up with, well, only things that are going to change are in this submatrix, right? So I'll have 2, 2, 1, 0 is the top row staying the same. Those 2 zeros are going to be unchanged. And then my second row is going to be unchanged. And then finally the last row, I'm going to take the entry from the last row and add it to the entry in the second row, right? So 3 plus 3, that's 0. 4 plus -2, that's 2. And 4 plus 5, that's 9. And now, if I wanted to think about moving on to the next submatrix, this -3 was our pivot, so our next submatrix would be this. It doesn't have any entries that are below it, so when we get here, we can see we're done. There's no entries. So you can see this is an echelon form, right? It makes the zeros staircase thing. And so we can read off like a simplified version of our linear system and figure out the solution. So to do that, usually this is called back substitution. And really all you're doing in back substitution is we're solving the equations. We're solving the linear system by using the equations. And we're going to start from the bottom. So, for example, that last equation says that 2 times x3 is equal to 9. That means that x3 is equal to 9/2, or 4.5. And now I can use that value in the equation that I'll get from the second row, which says -3x2 minus 2 times x3. Well, I know what x3 is equal to 5. So solving this for x2 is going to give me -14/3. Or if you like better, -4.6 repeating. Okay, so that's really it. That is the whole algorithm from start to finish. Let's do one more example just to make sure we've got this. and then we can move on to the full Gauss-Jordan algorithm in the next video. Okay, so here's another example. Let's follow this algorithm. So looking at this first column, we need to find the first non-zero entry, and it's down here. And we might need to swap rows to get that to the top. So that is the first thing we're going to do, is swap row 1 and row 3. And if we do that, we're going to get to this matrix. Now we have our new matrix after we've performed that swapping operation. And lucky day, the entries below our pivot are already 0. So we don't need to make any changes using those row operations to get zeros underneath the pivot. All right, so now we're going to move on to the submatrix below and to the right of the original pivot. And we're looking for the first non-zero entry in there, in the first column, so 6 is it. And then we have to ask what row operation do we need to perform to get rid of that 6 to make it a 0 that looks like row 3 plus or minus some multiple of row 2. Well, I think in this case it's easy to see. We're just going to subtract. And after I perform that row operation, we're going to have, let's see, I'm going to just start copying stuff that I know is not going to change. So I know that top row is not going to change, the top row of the submatrix. And then I'm going to take each entry in here and subtract from it the corresponding entry in row 2. So I'll get 6 minus 6, 1 minus 1, 3 minus 0, and 5 minus 0. The submatrix I'm looking at now has nothing below anything to try and zero out. So we're done. And this matrix is now again in echelon form. Right? The zeros make a staircase, and now we can read off the solutions and back substitute. One thing to note here is that this guy's going to have a free variable, so just mark off those pivots, x1, x2, and x4. These guys are the basic variables, and x3 is free. And we want to write down the solution now. We'll start at the bottom. We've got 3x4 equals 5. So 5 is, so x4 is just equal to 5/3, or 1.6 repeating. Then we can look at our next equation. We have 6x2 plus x3 equals 0. So x2 is free, x2 is basic, and x3 is free. So we need to rewrite this so that we're in terms, we've got x2 in terms of x3. So this, if we just solve this quickly, we'll get x2 is equal to negative x3 over 6. And then finally, we've got our last equation to solve, which says that x1 plus x2 plus x3 plus x4 is equal to 1. I know what x4 is. It's 1.6. x3 is free, so that's just going to be x3. x2, I need to replace that with the expression I have for x2 in terms of x3. So this is going to be negative x3 over 6. And then plus x1. And now when I solve this equation, for x1 in terms of x3, I'm going to get, let's see, x3 over 6 minus x3 minus 1.6 plus 1. And so simplifying that just a little bit, we'll have negative 5/6 x3 minus 0.6. So our full general solution we can now write down is this, negative 5/6 x3 minus 0.6, whereas x2 is negative x3 over 6, x3 is free, and x4 is 1.6 repeating. Okay, so that was kind of a mouthful, but hopefully you'll be able to get through this. It's a little bit tedious, but it does start to get really much faster after you practice it. I'll put a link up on this page for a website that does a really nice job of calculating these, so you can make up your own examples and try working them out. Okay, next video, Gauss-Jordan elimination.